Hello everyone, welcome back to my next tutorial. In this tutorial we are going to solve the truss analysis using Salome meca. Now we will see this truss model. This is a truss model we have taken. In this point we are fixing completely. Here we are giving a roller support, and this 3 point having a load of different loads of 280 kN, 210 kN, 280 kN and 360 kN. Now we will solve this case using Salome meca and ASTK. Now I will open Salome meca here. This is the case we are going to solve by using a Salome meca ASTK wizard and efficient with the help of efficient. Now first we'll model the geometry. Just go to geometry. This one is the geometry model. Here we can model it. First we'll define the line by using a points one by one. Go to new entity, basic and point. This view, first 0 0 and next point is here with a length of 3.6 meter. So in x direction 3.6, just apply, go to fit screen, you can see it. Now you can see there is a point we have created here, and the vertex 3 is the location of 6.3, 6.6 plus 6.6, so sorry 3.6 plus 3.6, so 7.2. Then just apply, go to fit again. Here we have created, and again we just want to add 3.6, 10.8. just apply, fit screen. Now you just see we have created first point, second point, third point and fourth point. Now this 4 point we have created. Now we will create these points in the distance of half of the distance and the height of 3.118 meter. So in y direction it is 3.118 meter. It is not changing, but x direction it is changing by 3.6 divided by 2. Now just take a calculator, not to. So 3.6 divided by 2, that's it, 1.8. Now we'll add one by one. So this one is a 1.8 distance, x distance is 1.8 and y distance is 3.118. just apply. Now just go here, we just want to add 1.8 with 3.6, so 4.8 and 5.4. now here you can see plus 3.6, sorry 1.8 plus 3.6, 5.4, just put 5.4, just apply. I think calculator is not required, it seems. Now we can add one by one. Now just see the next distance is, add 3.6 with this. Now 8 and 9, the distance of 9. Now just apply and close. Now we have created all the points. Here you can see. Now we'll create a line. Go to new entity, basic, line. First one is vertex 1. Then go to vertex 2. Just apply. From 2 to 3, just apply. 3 to 4, just apply. Then this is just change into 1 to 5, just apply. Then 5 to, yes, there is a line here and here. Here also we can choose, just apply, sorry. Vertex 5, Go to 6, just apply. Go to 7, just apply. Go to new entity, basic line. Just view this coordinate, then only you can check, easily put. Now just go to new entity, basic and line. Now which vertex, this one we can choose. And this one. Just apply. Now we just want to put like this. So this node to this node, just apply. And this node to this node, just apply. From here to here, just apply. From here to here, just apply. Finally from here to here, just apply and close. Now we have modeled this complete stress. Now we can make complete stress into a single wire. Just go to the model. It is having a section of 0.1 and 0.1, same section. So now just select all the edges, just 1 2 3 4 5 6 7 8 9 10 11. There are 11 edges. Just add one by, just select all, go to new entity, build wire, just apply and close. Now we have built the wire, just so only. Now we will save this file. Go to file, save as. Here I am just saving it. Now we have created the model truss we have created. Now we just want to create groups to apply the boundary conditions. So here and here we just want to apply fixed boundary conditions. Create group, point group. First we'll create edge group. This one is the beam. Apply. Now go to point group. Here I'm just naming as fix all. Just apply. Here just add. Here I'm naming it as roller. Just apply. These two groups I have created. Now we just want to group 1 2 3 4. This 4 group I want to create. I'm just naming as F1 280. It is easy to understand. First one added. This is FY1 underscore 280. This one is also FY2 underscore, the load value is 210. To easily apply the loads, just apply. And this one is just add. This one is FY3 underscore, the value is same 280 again, 280 again, 280 again. Just apply. Finally this node, just add. This is the FY4 360. FY4 360. Just apply and close. Now this beam, it has a beam element. To assign the element property, I have created element groups. Then these two which I have created fix all and roller support. I have groups I have created to apply the fixed support and roller boundary condition. This one is the FY1, this node. FY2 is this node. FY3 is this node, and FY4 is this one. To easily apply the load, I have created the load group like this. Now we can save this file. Now we have created the groups. Now we'll create a mesh. Just go to mesh model here. Select this wire one. Go to mesh, create mesh. This is actually 1D wire discretization. Choose the hypothesis as local length of 1. It is showing. I'm just giving 0.5. Just say OK. Apply and close. Just right click here, compute. Now 84 nodes I have created. To check the node how it is generated, modification, add node. This is the way node we have created, node and edges. If you want to increase the number of node also, we can go for by reducing the size. This is enough to me. I'm just closing here. I'm just saving this file by Ctrl S. Now we'll export this file. Right click this mesh one, go to export in MAD format. The same folder, I'm just saving it. Now we have created the mesh. Then we just want to create a setup to solve the case. So just there is a software called Efficient. I'm going to use it. Just right click this Efficient file and open it. So this one is a linear static analysis. Need not to change anything in this first window. Go to analysis type, change this into a beam. Now go to material. This is a carbon steel only. CS, I'm just naming it. This Young's modulus in meter, I just want to specify it. 210 e power 9. 0.3 is the Poisson ratio. Density is not required for the linear static analysis. Anyway, I'm just specifying this value. Then assign to all. Just add. Then go to element type. This is a beam element, rectangular section, and cross section is point. Assign to. Assign to, we just go check it. We have named a beam element in small. So just copy and paste it there. It is better to avoid the error. I'm just copied it here. I'm pasting here. Then height 0.1 and width also 0.1. Height and width. This is actually for hollow section. These two property. This is actually solid section. Here I specified it. Just add it. Now we have created the element and assigned the element property to the model. Now go to boundary condition, mesh group or node group we can choose. I'm just going to choose node group. Boundary condition name, any name we can give. One by one we can give it. So first one is fixed 1 because fixed assigned to the group name of fix all. Just copy and paste. It is better to avoid the error because if you are giving a small, if you are giving hyphen small letter, we have to use the same way, same pattern we have to use. It is case sensitive. And now we just fix it all to arrest all the degree of freedom. We have to give 0 to all translation and rotation. Just add it. First group we have created. Second is the roller support. So now boundary condition name is roller. We can type it also, but it should not be properly. We have to type it. So this rollers support, roller 1, any name we can give actually. So he is assigned to the roller. This is here only we have to give the group name, and in roller support just go to the case. Y direction we just leave it. Roller support means it has to move freely in X direction. Remaining direction we just fix it. That's it. So free the X direction, remaining you fix it. Remaining we are arrested, it can move X direction freely. Just add it. Second boundary condition also we have done. Now we just want to apply the load. Just go to the PPT. These two we have done. We just want to apply 4 loads. So one by one we'll apply by using a wizard. Go to loads. This one is the force on the node. Load name, load y1, assign to, this is the first one. Just copy, paste it here. So this is Fy 280. In y direction minus 280 kilonewton. Just add 3 more 0 because we have to apply it as in Newton. Remaining we just make it 0. We can give it as 0 also. By not specifying, it will not show anything. So only which one you are specifying, that only it will apply. The first one we have done. Similarly second one, load y2, assign to this group. I'm just going to copy and paste it here. In y direction minus, this one is a 210, 3 more 0 we have to apply in Newton. Just add. Again load y3, assign to this one, just copy and paste it in the assign to, and y direction minus 280, 3 more 0, just add. Now again load y4, any name we can give for pattern. I'm using it this way. Then final load group is this one, just copy and paste it here, and in y direction minus 360 Newton. So I have applied all the loads. Now we can go for output. We just want to save all the results, add all, save this command file, just navigate this file to the specific folder. So I'm just naming as any name we can give. I'm just static.comm. So this is writing is done. Just close this wizard. Now just go to the folder where you have saved the results. Now see, so we have created the mesh file, we have created the command file. Just open the command file, see one by one. We are reading the mesh file. This is just assigning the model. This is actually a mechanic beam element. POUDT is nothing but a beam element. So elemental property we have specified here, the section of rectangular section with the cross sectional value of 0.1 and 0.1. Material property we have defined, and we have assigned the material property to the mesh. Then fixed group and roller support we have created, and 4 forces we have created. This is a solver. It's a mechastatic is the static solver. We have taken all value into the solver. Now this one is to calculate the derive the values. The solver, it will calculate the displacement. It's a primary variable. Remaining variables we have to derive from the primary variable. So here you can see resulted is the result. It's taking the primary results and it's deriving the other variables and it's saving the results. Now using a ASTK wizard, we'll run this case. Now I'm just saving this file. Now go to tools, plugins, code aster, ASTK. Just OK. So this is the wizard for ASTK. For EC, I'm just keeping like this. Now we have to use these two files, mesh file and command file, to run the case. First I'm navigating this folder to the same folder, pictures, code aster, save. This is, we can save this file, save it. Any name we can give. I'm just giving this simple name. See, ASTK file is generated. It will generate the file whatever we are specifying it. So first one is the command file. Next one is for mesh file. Then message, error. We can use any order. Resu. The finally is a RMD format. So resu RMD. RMD is the output format to view the result in. These are all output format. Message, error, resu, RMD, all are output formats. So now we can name it one by one. /. So same name we have to give, static.comm. Then /. mesh_1.med. Then /. message.mess. /error.err. /resu.resu. Then finally result.rmd. Any name we can give. These two only we have to give proper name, whatever name we have used. These are output file name, whatever file name you wanted, that name you can give it. I'm just for easy understanding, I'm giving the same like this. Then memory. So how much memory you have, RAM memory you have, you can type it here to use the memory for solving. I'm just using 1 GB is enough for this case, and 15 minutes is more time for this simple case. So interactive follow up, just save this file before running, then just run it. Now it is solved. First read the message file. This is the correct way of doing it. Here also you can see it started reading the mesh debug. reading the mesh. From the mesh, whatever it is there, it is and typing here. It has groups, elemental groups. It is segment of 88 segments, 84 nodes, and model. It is a beam model. Everything it's reading and it's solving. Here you can see this is a solver. It's solving and saving the results. It's come up with the alarm. So there is no issue with the alarm. Now just go to check the output results. Yes, see the result.rmd file is generated and saved here. Now we can open this file using a paraviews to view the displacement and stress. Now just go to here, change this into paraview model. Now just right click this building and open. Go to pictures, code aster, this one. Choose this result.rmd, just say OK, just apply. Now we just go here, displacement. So this is the way it will get deformed. Now just y direction deformation you can check. Generate vector, just apply. Just give some scale factor, just apply it. So this is the way it will deform. Now we'll change this color pattern into blue to red rainbow, just close, and I'm just changing this into a gradient background. Now we'll animate this, then only we can easily see how it is. Just say OK. See here it is completely fixed. Here it has to roller support. It can move in x direction also. Now we are applying a force, so it is bending in this way. See, so this is the way a truss will work. It's kind of a bridge truss. Now the displacement is correct. Whatever the load we have applied, the structure is becoming in the same manner. Now we can check the stress. SIPO NO. This is a normal stress in the every beam. Now this also we can change the color. Just apply and close. So we are getting the whatever the element you can see. This three element is getting more stress of 30 megapascal. This green, these three element is getting is same 30 megapascal in compressive load. This compressive element will not get failed, but this tensile element only will get failed. So like this we have to check the model. So now we have done. Thank you for watching my videos. Please subscribe my channel for more videos. Thank you.